So this is the electromagnetism topic, so it's only makes sense that we look at the interaction between charged particles, electricity, and magnetic fields, electromagnetism. And a uniform magnetic field is going to be formed by a magnet of some kind of polarity pointing down and a different magnet of the opposite polarity pointing towards it like this. And the magnetic field will go from north to south, up and down as shown. Very similar to a uniform electric field between two charged plates. There's going to be a curve to the magnetic field on the sides, so we're not talking about the parts on the side, just in between. Um, and the interaction between charged particles and uniform magnetic field. So if we put a charged particle in this magnetic field, what is the interaction? The interaction is absolutely nothing. Nothing happens at all. The charged particle does not care about this magnetic field whatsoever. That is until it starts moving. If you have a charged particle moving in a magnetic field, let's say it's moving this way, it's actually going to be influenced by that magnetic field. It's going to experience a force. And we have a cool way of working out the direction of that force. It's called the right hand push rule. So I'm going to attempt to draw a hand here. I'm stuffing that up. I need to draw a right hand that's going to be a left. So I'm going to draw a hand with the palm facing up. So drawing my hand, yep, good. So 1, 2, 3, 4, and the thumb that way like this, good. Okay, and this is the palm of the hand here. The palm of my hand has a line across there and a line across here. Beautiful. Okay, so in this right hand palm rule, the fingers are representing the magnetic field, which is B. The thumb is pointing sideways in the direction of current, I, and the palm, the direction the palm pushes. So in this case, this palm is about to give me a high five. That palm, yep, that palm is pushing in the direction of force. So I can't really, I'm going to draw it out this way to the direction of force. You just have to imagine it coming out of the page towards us. Okay, so magnetic field's the fingers, thumb is the current, and the push is the direction of force. So what force is this electron going to experience here, or this negative charged particle? First, we need thumb in the direction of current, okay? And the electron is moving this way, but current is defined as the movement of positive charge, so it's actually going to be this way. We need the fingers in the direction of magnetic field. Magnetic field is down. So I need somehow to get my thumb to the right and my fingers down while my hand is flat like this. And so it's either going to be an awkward upside down like this, or I could bring my hand around like this. Either way, my thumb is now pointing the correct direction. So are my fingers, okay? And my palm is pointing towards you. The force is, well, my palm's pointing, my palm's pointing towards the screen actually. So in this case, the force is going to be into the page there. It's going to push into the screen and it's going to curve around because of that. Let's look at a slightly different scenario where we can see a better example of it. For this example, I'm still going to have let's say we have a positive charge and it's moving across. That's its velocity, and it's moving through this kind of magnetic field. Let's say it's a magnetic field that is into the page, okay? And into the page magnetic field looks like this. It's crosses because it looks like the back end of an arrow. It'd be dots like the pointy part of the arrow if it's coming out of the page. So we have direction of current. That's the same direction as the positive charge. We have the magnetic field that is into the page. So I'm pointing towards the page, and now the force is going to be upwards. So this is going to experience an upwards force like this, and we're supposed to compare this to other examples, uniform motion and the interaction of charged particles with electric fields. Just like when we looked at what happens in an electric field, this particle is going to move. It's kind of going to start looking like projectile motion. It's going to start curling around this way instead of moving straight along there. It's not exactly like projectile motion, though. It is more like uniform circular motion. I'll tell you why very, very soon. But first, let's look at this equation. So the amount of force, we've looked at the direction of force. Now we can calculate the amount. It's equal to QV times B, as long as V and B are perpendicular to each other. In this case, they are. Velocity's to the right, magnetic field is into the page, okay? As long as when you're using the right-hand rule, as long as this is a right angle here, then those two things are perpendicular to each other, because the velocity is related to the direction of current and magnetic field is the fingers here. So as long as these are at right angles, if you get a situation where it's starting to come up like this, right, it's going in the same direction as the magnetic field or in the exact opposite direction, in those two cases you have zero force. If you have something in between, you have slightly less force, and you can work that out using 𝑞𝑣𝐵 and adding in the sine theta, where theta is going to be the angle between the current and the magnetic field, or the velocity of the particle, I guess the velocity of the positive particle and the magnetic field. Okay, so Q is the amount of charge for a proton. You can check your data sheet to find out how much charge is on a proton. Velocity, you're going to need to be told the velocity and the magnetic field in order to work out the force. Velocity is in meters per second as usual. B, magnetic field, is in T, Teslas. That's a capital T for Tesla. Okay, usually if you've got a magnetic field of 1 Tesla, that's a very, very strong magnetic field. So just be aware, however, questions might not be realistic when you come across them. So let's reset again. Let's think about how this is similar to uniform circular motion. So if we have a big enough, magnetic field, say it's really, really big, it's taking up all this space, and we have our proton, and our proton's moving this way. So we quickly go, boom, magnetic field, force is up. So right now it's experiencing a force upwards, let's say to there. All right, so it starts to move in a curved path. It's moving in a curved path. By the time the proton is in this position, its velocity is now this way. Okay, its velocity that way, well, its velocity is that way, so the current is that way, magnetic field's into the page. Hello, the force is no longer to the right. The force is now, the force is no longer upwards. Force is now to the left. So now our force is pointing to the left, and it's going to curve around that way. And you might see where I'm going with this. Once it's in this position and its velocity is in this direction, now if we have velocity, positive charge, current is this way, fingers, magnetic field are into the page, my palm's pointing down, the force is now down. Hello, because of that downwards force, it's going to curve again. And, surprise, surprise, eventually it joins up and it moves in a perfect circle. This is uniform circular motion. What is the force, the centripetal force keeping it moving in a circle? That is the force we calculated before, the force due to the interaction between charges and magnetic fields. Okay, this is the same as any other example of circular motion. It can be a moon moving around a planet, okay, with the force of gravity pulling it in. It can be a ball on a string held by a person. It's held to their elbow apparently, and if they swing the ball around their head, okay, it's the tension in the string forcing the ball in. It could be a car turning around a road with its wheels causing friction with the road, pulling it inwards. Either way, you always have this force pulling towards this central point. This force pulling towards the central point. Again, the force pulling towards the central point. That's what happens with all uniform circular motion. Because of this, we can use the uniform circular motion equation. The centripetal force is equal to half mv squared. Sorry, it's equal to mv squared over r. Okay, and that centripetal force, because it's caused by this interaction, that centripetal force is also equal to 𝑞𝑣𝐵 sine theta, or 𝑞𝑣𝐵 as long as both of them are perpendicular. And so you can change your equations around. Since both forces are equal to each other, you can say that mv mv squared over r is going to be equal to 𝑞𝑣𝐵. And very nicely, you can cancel this v out here with that squared there. So you get mv over r equals qv. And that could be used to solve problems that seem difficult to solve. It might look like you don't have enough information or the wrong types of information, but you can actually solve these problems. Okay, that's all for now, and that's the end of the first section of electromagnetism.